Hi there, Mr. O here with another in a series of Structures in Action videos. In this video, we're at the site of the Gateway Ice Facility located at the corner of Fruitland Road and South Service Road in beautiful Stony Creek. When complete, this structure will feature 3 ice pads, an elevated running track, a 5-star fitness, and a Don Cherry's Grill, all located inside. The structure is 49 foot high at the peak and clear spans 130 feet over the ice pads. This structure contains over 600 tons of structural steel. Now let's go on site. In order for any project to be successful, we need 3 elements. We need great design, we need great materials, and we need great construction. And the construction is really the vital element. It's really a critical part of it, and it's where I want you guys to be. I want you folks to be thinking all the time about the people in the field and what they have to do. So what is the order now that we come to site, and what is the order that we're going to follow? Well, typically there'll be maybe some demolition, maybe some clearing and grubbing, that sort of thing. So after that, usually the first people in are the concrete contractors, and they're responsible for excavating and placing the foundations for the structure. Here you can typically see one of the foundations in place. Its placement is absolutely critical. The center to center between this column and the next column has to be right on. The elevation of the top of concrete has to be right on within reasonable tolerances. And you have to keep those tolerances in mind. So we take a look here and we've got the concrete foundation. If anything, you want to keep it on the low side because you can see what happened here. The iron workers come in, they set their base plates. The anchor bolts were already in place with the concrete foundation folks, and they set the elevations accordingly. And so now what they've done is they've come here and they've packed a grout mix underneath the base plate here so that the elevation of the top of steel here is absolutely correct, probably within 1/8 of an inch or 1/16 of an inch even. Now what will happen is the steel column that will come into place here will come down, will sit down, they'll torque up the bolts, and we're ready to go. Wow, this is a big space. Amazing thing, these rigid frames. So the owner architect comes to you and says, we want to build an ice pad facility. What are the questions that come to your mind in the way of need for the structural facility? Well, one thing had better be long, clear spans. We can't have that post coming down at center ice to carry vertical load. But we also have another load to carry, and that's called lateral loads, or the horizontal loads, or what we commonly know as wind loads. We have to carry those as well. So for the vertical loads, we can use big deep beams. We could use a truss, or we could use a rigid frame system. But when it comes to carrying those wind loads now, we can't have any of our standard systems like cross bracing or shear tubes or shear walls. We can't have those interfering with the clear span required for the ice rink. So that's where the rigid frame comes into play and is one of the best systems to use for both lateral and vertical loads when these long clear spans and that wind resistance is needed. As we know, one very effective and very economical way of resisting those horizontal wind loads is vertical bracing. And you can see in this structure that it's utilized, but only on the perimeters. And it's nothing more than a small diameter steel bar that's going to be used in tension, and it will take those wind loads from the roof all the way down to the foundation. But obviously, we cannot cross brace in the middle of a wide open span required for a hockey rink. That's where the rigid frame comes in. Now, I've already mentioned that any great project needs 3 components. It needs great materials, it needs great construction, and it needs great design. Well, let's take a look now at the materials in the construction phase of this. In North America, typically, the labor force is expensive, the materials are relatively inexpensive. So now, take a look at the beams and columns in this rigid frame structure. You can see that they are not standard prismatic sections, what we call, rather they are tapered. That means somebody had to cut these plates to suit and somebody had to re-weld them up. That typically is expensive. However, when we get into the case of a rigid frame such as this, we get into what we call pre-engineered buildings. That means this is more or less an off-the-shelf kind of structure. In other words, there's a company somewhere out there that supplies nothing but these types of structures, and that's what makes it economically viable. What you can see here now in this type of a structure is lots of material where it's needed, and less material where it's not needed. Think about the bending moment diagrams. Think about the shear force diagrams. How they vary, that's how the steel varies. Where the bending moments are large, we've got lots of steel. Where the bending moments are small, we have less steel. It becomes economically viable to make this kind of structure if that's all you do. So these tapered sections that you can see in a rigid frame are typically expensive because somebody has to cut them and somebody has to weld them together. So they might be economically unfeasible, except for when that is all you do. When you make these sections, and this is an off-the-shelf type of structure, then you can put the material where it's needed and take it away where it's not needed. So at the top of the column up there, you can see that heavy haunch. That's a heavy bending moment area up there. And that's not only due to the vertical loads that are going to be on the roof of this structure, but also the lateral loads that are pushing against this structure. It's that solid, rigid joint up at the top of the column that gives this thing both vertical strength and lateral strength as well. That means we don't need any vertical cross bracing or any other means of lateral load resistance, such as a shear tube or shear wall, in order to resist the lateral loads. That's going to leave this span wide open for the ice rink. The roof system in this structure is a very common and very inexpensive structure. You can see that we've got what we call cold rolled purlins with some diagonal braces coming off the ends to stabilize them. Sitting on top of that, you can see the decking already in bundles there. It's ready to be placed. I've always said that there's economy in repetition. If you can design one part and use it 500 or 600 times in a structure, that's where the economy comes from. You can clearly see that in action here. Not only in the rigid frames, they repeat themselves, but the roof system. There's one purlin used 500 times. So here's a question for you now. You're the designer. Tell me what the load pattern is on each one of those purlins. If you're the designer, you need to know what the load is, because then you're going to draw the bending moment diagram, you're going to draw the shear force diagram, and then you're going to design it. We call that assigning a size. So here's another question for you, keeping in mind the practical side of things. How do you erect these structures? You know we can't ship them in one piece, so how do we get them into the field? We have to remember that the contractor has to be able to put these up. And of course today is a gorgeous sunny day, 25 degrees Celsius, but he's also here when it's minus 20 in a driving snowstorm. How can we make that work? The answer is simple. We break them down into simple pieces and we put them back together again in the field through splices. Let's start at the exterior column. You can see the exterior column is a standalone by itself. At the top of that column is a splice. The first roof beam section splices to the column. Follow further along, maybe 20 feet or so, 20, 30 feet, you'll see another splice in the roof beam system. Follow along again, another 20, 30 feet, you'll see another splice. And then if you go one more section, you'll get to the center row of columns, and that roof beam cantilevers on both sides of the column. And then the whole system repeats itself over the next ice pad. There's economy there. So if I take a look at what we have here, we've got a beam that's probably 5-6 meters long. And in class, our job is to draw the bending moment and shear force diagrams and determine the reactions. Why? So that we can design it. Now in the classroom, we take this kind of a simple bolted connection and we draw a little triangle underneath it and we call that a hinge. And in reality, that's very true. On the other hand, what we draw at the other end of the beam usually is a little triangle with rollers underneath it, indicating some sort of a sliding connection. Well, in fact, I don't think we could even say that this is anywhere near a sliding connection, but the truth of the matter is that it makes our life so much simpler in terms of structural analysis. And so we can make that assumption and come up with an answer that's close enough. Structures is a world that's plus or minus 10%. We don't need to be right on, we just need to be close enough and on the right side of conservative. So when you take a look at the roof beams in the little lean-to structure, the question becomes, why would anybody cut diamond-shaped roof beams like that? It's economically not feasible. But the truth is, when you do this for a living, it is economically feasible and it makes a lot of structural sense. So now the question for you is, why is that diamond beam shaped the way it is? The answer is simple. Take it out, draw a straight line on your paper, put the load pattern on it, and draw the bending moment diagram. That's where you'll find the answer. So here what you see now is a typical classic simply supported beam in place with bolted connections to the column at either end. In class, we'd draw this with a little diamond hinge at one end and with a little roller at the other end. Well, clearly there is no roller here, but that simplification will make our life so much easier in terms of analysis, and it will produce an answer that's close enough and safe. So we know that every structure works 100% when it's 100% together. But what happens when it's Friday afternoon and it's time to knock off and the structure is not together 100%? Well, here's one example of what we can do. This is typical of what the iron workers would use to cable a structure to provide some lateral bracing while the structure is incomplete. The iron workers will also use this to level and to plumb the building to make sure that everything is in place before they start bolting up. So as you can see, this is a tremendous structure with its own unique set of needs. You, as the structural designer, have to be able to meet those needs. That means you have to be able to reach into your bag of tricks and be able to provide a structural system that will meet the needs and the function of the facility. In this case, long clear spans was the key.